Hi, I'm Dr. Tim Coleman with the University of Alabama in Huntsville, talking a little bit here about poster number 175 in the Mesoscale Processes Conference at the AMS Annual Meeting. Spatiotemporal variability in wind shear and helicity due to various processes. My co-author on this paper is Dr. Kevin Knupp, also of UAH. We both work at Swirl at UAH. And basically what this poster is about, we know that wind shear and helicity at the lowest levels continues to be shown more and more in the literature to be a factor in tornadogenesis, and it may be impacted by processes that we don't normally think about, like the typical, thermal advection, low-level jets, celebrate winds going into a deepening low, things like that. So these smaller scale processes need to be examined in depth. And the three we're going to look at that are beyond those synoptic meso-alpha processes we think of are the afternoon to evening transition, also known as the EET, sometimes in literature, early evening transition, the rain-induced transition, and spatial differences in roughness length. The first one we're going to talk about is the rain-induced transition. We're starting out with a very elementary graphic here that shows how without friction you have geostrophic wind. With friction, because the frictional force slows the wind down, it also tends to back and flow across the isobars a little bit. So friction causes slowing and backing of the wind. Now, this occurs because of friction with the ground. Now, any process that causes cooling near the surface will increase the stability of that layer and decrease the vertical momentum flux, or the vertical flux of horizontal momentum, which tends to transport the effect, for lack of a better word, of the friction aloft. So what happens is the frictional forces tend to get concentrated at lower levels when the air gets stabilized, causing a slowing and backing at low levels. And then aloft, those frictional forces don't really get transported up there as much to the upper part of the boundary layer. So winds there, without that frictional force, tend to accelerate and veer due to the Coriolis force. One example of a process that causes this is the rain-induced transition. Especially in environments with low dew point depression, low LCL, high relative humidity, weak convective showers may precede a QLCS or a supercell. In the case shown here from Coleman et al. 2018, a tornado formed in an environment that really didn't appear to be optimal for severe weather, wound up producing a significant tornado and a lot of residential damage in the southwest suburbs of Birmingham, Alabama. Now, this tornado was associated with a narrow band of enhanced dew point and cape due to frontogenetical forcing. However, as noted in that paper, there were also light rain showers between 30 minutes and 2.5 hours prior to that tornado in the area where the tornado occurred. If you look at that graphic, the area in the ellipse is the area where that's a QPF graphic, and you can see that QPF graphic ended about 30 minutes prior to tornadogenesis, and you can see there's an area of showers that moved through there. This happens a lot. Rainfall amounts were not that heavy, about 0.75 millimeters, but local stations reported a cooling of about 2 degrees Celsius, which was associated with some increase in stability. Since these surface speeds and gusts decreased at one of these mesonet stations in the hour after the rain showers passed, that's somewhat of a verification that you had winds at the surface decreasing, unlikely that the winds aloft would have decreased associated with these rain showers. So there was a decreased turbulent flux of momentum. This indicates the possibility of increased storm relative helicity due to the rain-induced transition. And if we look here, tornadogenesis occurred around 2341 UTC. Even at 2325, you can see some showers out ahead of it. You see additional ones, storms or showers out in the inflow region of the supercell at tornadogenesis time. We don't have enough adequate observations for this rain-induced transition to prove it, but our theory right now is that the showers in the inflow or moving through ahead of time tend to stabilize the boundary layer just enough that it increases the wind shear. However, it doesn't really affect the cape because it's very minimal cooling. Okay, the second process we're going to look at is the afternoon to evening transition. Basically, when surface temperatures start to drop in the afternoon, late afternoon, when the heat flux becomes negative, you start to get a stabilization in the lower boundary layer due to this cooling. An inversion often forms. And this entire period from the beginning of cooling, usually about 2 hours or so before sunset, through the end of that rapid cooling is known, which is about 2 hours after sunset, is known as the afternoon to evening transition. This causes, similarly to the RIT, a slowing and backing of surface winds. Again, it stabilizes the lower levels, so you don't get as much of that vertical momentum transport. So surface winds tend to slow and back, and winds above the surface, or up in the higher parts of the boundary layer, tend to increase in speed and veer. Here's a schematic of that. Basically, pre-AET, you see a photograph here, and then post-AET, you notice that the winds have backed and slowed a little bit at low levels, but up here at 1 kilometer, they have veered and accelerated. Both of these processes tend to lengthen the hodograph, increasing storm relative helicity. Now, in this one case example I show here, basically, looking, the storm relative helicity during part of the AET from 1 hour prior to sunset to 2 hours after sunset increased from 300 to 600. So basically a doubling of 0 to 1 kilometer storm relative helicity. These time height sections over here of wind direction and wind speed show winds at low levels tending to back, and at upper levels they veer initially, but then they tend to stable out. In the speed, you see wind speeds at lower levels slow a little bit, and they speed up at upper levels. And again, and this is between the surface and about 1,000 meters AGL. What we did here is look at a climatology of bad wind profiles, thousands of them, and threw in the surface observations. We chose 4 radar sites where an ASOS is located, so we could have surface to 1 kilometer flows, and that was Birmingham, Fort Smith, Paducah, and Wichita. Any AET where between 2010 and 2018, when a tornado watch was in effect, we looked at those to isolate days with severe weather potential, looked at time series of SRH, and generated using bunker storm motion and surface to 1 kilometer AGL winds over time series. Now, any days where we had a disturbed afternoon to evening transition, convection moves over the radar site and the surface station, fronts, density currents, atmospheric waves, we threw those out. But we wound up still with a large number, 60 undisturbed AETs across these 4 radar sites. And on average, as you see at every one of these stations, all 4 of them, there tends to be an increase in storm relative helicity on average between 2 hours before sunset and 2 hours after sunset. And the average of all 4 stations, all 60 events, the storm relative helicity increased by 142 meters squared per second squared during the AET. Now, again, what we're working on right now is going back to look at how much of this, given that tornado watches were in effect, was related to changes in the geostrophic wind profile versus how much of it was related purely to AET processes. Likely it's going to be a combination of both, and the AET is not responsible for that full 142 meters squared per second squared increase, but it's going to be responsible for some of it. We've heard about 6 o'clock magic and things like that for a long time. There are a number of things that happen during that AET. Finally, we're looking at the spatial variations in friction. And so we've talked about, this is a more of a purely, The afternoon to evening transition is temporal. This is a spatial variation in storm relative felicity. Recently, an article published by myself, Kevin Knupp, and Preston Pangle in EJSSM in December. And this is basically, this material in section 4 is all taken from that article. I encourage you to read that article. But basically, surface roughness is a good proxy for the force of friction on surface layer winds. You can see different wind profiles here, from blue over water to the dark green over a forest. And what you see is, the winds near the surface are slowed down greatly, but then at the top of the surface layer, they're the same, 10 meters per second. So it creates a lot more wind shear in areas that have higher roughness length. So the first thing we did look at here was on 28 days with southerly low-level flow. The 10-meter AGL wind was compared for the Huntsville Airport, which is in an open grassland area with a roughness length around 0.24, and the wind at UAH, just 15 kilometers up the road in a more urban area, the roughness length 0.41. Again, these roughness lengths come from the HRR model. The scatter plot below for several thousand 15-minute averages that were non-overlapping. What it shows is that generally the winds at Huntsville Airport in the lower roughness area were almost always higher than the winds at the UAH berm in terms of 15-minute average wind speed. Can't really discern much about the wind direction, though. You would think the winds at the berm, which are lower, would be backed relative to a more veered wind at the airport. That does not come out in this. However, if we looked at 12 pairs of simultaneous vortex southeast soundings during 3 2020 IOPs, one of those actually was in 2021. That's an error there, but they show the difference clearly between a site at Cortland, which is located 65 kilometers southwest of UAH, and again, its HRR roughness length is 0.27, compared to that urban roughness length at UAH of 0.41. At 9 of those 12 times on 3 different days, the storm relative felicity was higher at UAH, where the roughness is higher, than at Cortland. The average difference was about 94 meters squared per second squared in terms of a higher SRH in the urban area with higher roughness than at the lower roughness at Cortland. Now again, with those being that far apart, we're going to have to look at were there synoptic forces or meso-alpha scale processes involved in creating that difference. But 9 out of 12 is pretty convincing that there is some effect from the higher roughness length causing more storm relative felicity. And finally, CAMs like the HRR, they are showing this increased helicity based on it. The map you see here on the left is the Mobile and Pensacola Bay region after Hurricane Sally had moved northward away from the area. It's now in northwesterly flow. The contoured colors are showing the wind speed, and you can see it's much larger over the water, say over Mobile Bay, Pensacola Bay, and the Gulf, and slower over the land there in Alabama and extreme northwest Florida. But that blue dot is a location over Mobile Bay. The green dot is a location over Baldwin County, Alabama, over land, and photographs from each of those is taken at that time. And you see over the water, the 1 kilometer winds are very similar to what they are over the land. However, the surface winds over the water are much higher and slightly veered, whereas the winds over the surface are much lower and slightly backed in direction. So this shows that even the CAMs, like the HRR, are picking up on this increase in storm relative felicity and lengthening of the photograph over a higher roughness length area like land versus a lower roughness length area like water in a situation with fairly uniform northwesterly flow. So if you have any questions, don't hesitate to email me at coleman@nssTC.uah.edu or my partner Kevin at nssTC.uah.edu, my partner in this paper, and we'll be happy to answer questions for you. And thanks for stopping by.